Okay, so we now are we're learning now about exponential growth and decay. And this is the topic mainly discussed in section 4.5 of the textbook. Alright, so before we can start, let's have a quick basic idea of what it means by exponential growth and decay here. So, a growth is when a population gains its size. So you can think of, it's a natural thing that happens everywhere. The population of a certain country is increasing. We live in the United States, we're increasing in size, our population is increasing, so that is a growth, right? Or you can think of bacteria is growing, and you can think of the population of fish that live in fishes that live in a pond, it's also growing. So population, that is a growth is when a population gains its size. And then also, similarly, a decay is when a population loses its size. So now, a lot of time you can see when you can see a decay, it's like, think about in maybe if some of you are taking chemistry, then you can think of for any certain type of chemical substance, when you leave it there for over time, it's naturally breaking it's down. Or you can think of a human body, after we die, our human body keep breaking down and we lose our stuff. So technically that's what a decay is. So now furthermore, an exponential growth or decay is when the growth or the decay can be modeled by the equation A equals a sub 0 times e to the kt. So what you're looking at, this equation here, what you can see is the equation here is an exponential function. And so that's why we call it an exponential growth. So basically the growth here has to follow that equation. So you can notice the exponents here, the power k, the power kt right here, we have positive k right there. Now in case it's a decay, then the function for that is going to be a equals a sub 0 times e to the minus kt. So just the basic idea here is that when it's an exponential growth, then it's e to the positive kt. When it's exponential decay, then the function to model that is going to be a sub 0 times e to the minus kt. And our k here is always a positive number, so keep that in mind. Alright, so as a quick explanation of what the variables are, as a quick explanation of what the parameters here in the function is. So we got a sub 0 is the initial population size before the growth and decay take place, right? So you can think of like say right now at this moment you are starting to look at your bacteria and at the bacteria populations and say, so that is our initial, that is the role of a sub 0. The initial population size, okay? And then k is the growth or the decay rate, like say how fast the growth is or how fast the decay is, okay? How fast the breaking down process is or how fast the growing up process is. And then t is the variable for time, depending on the unit of time in the problem. So sometime in our problem we try to measure the growth in times of units seconds. Sometimes things can happen as quickly as in nanoseconds, but then sometimes things can take as long as in years and millions and tens of years, thousands of years. So once again, t is time. and a here that we're looking at is different with a sub 0. Now a sub 0 once again is the initial population, the starting point population. A here is the general A. It's a growth or the decayed population at any time after the initial population. So now, generally as a big picture here, then in any exponential growth or decay problem, we must always first compute the k value. And the way to compute the k value, it really varies. It varies depending on the problem, but then when we get to some of the example, you will see how to find the k. But remember, keep in mind one thing: k must always be computed first, and k itself has to be the positive value. It's always have to be the positive value. usually the initial population A sub 0 is given. So that's something that we can be released off a little bit. And then last thing, once the rate, which is the k value, once the rate is computed, we normally see the following questions about the population. So one of the big questions is always write the function that models the growth or the decay. That's one of the common questions. Now the next common question that we usually encounter is that what is the population size at a particular time t? So notice the time t here is the time sometimes t after the initial population. Okay? And then another common question regarding to the population here is how long or how much time does it take to reach a particular population size? So you can think of like say right now the the US population is about like a few hundred millions, right? So that is the initial population, and you want to say, and you want to come up for yourself a question like, how long it's gonna take to reach like, double the amount, or how long is it gonna take for the initial amount of population? Right now, it's gonna be about 5 times as much. Okay, so that is the third question, the third common question that we're gonna be concerned about in an exponential growth or decay problem. And then the last but not least, another common question regarding to is that in case that sometimes it happens sometimes, but in case when a sub 0 is not given, sometimes yes, sometimes it happens that the initial population was not given. So we do have a common question that how much was the initial population? So it could be like we start monitoring the population of bacteria since 5 years ago already. But then right now we know at this moment it's going to be this much. But then how much was it when we start out the experiment? So something like that's going to be expected. Okay, and then now another concept that is important in these topics of exponential growth and decay is the half-life concept. Now half-life, what is it? Half-life only in a decay problem. Okay, half-life once again is half-life is we only deal with the half-life problem in a decay problem. Okay, so half-life in a decay problem is the time it takes to have only half of the original population remains. So now you can think of like say there are some chemical substances losing itself, or think of our human body. Once again, when we die, our body here breaks down, and we would like to know how much time it takes for our human body here remains only half of it. So like say it could be long as in hundreds of years, but it could be thousands of years to have only half of the human body here remains. And once again, I'm talking about a decay process. Okay, so that is a half-life. So half-life once again is the time it takes to have only half of the original population remains. So now fortunately we do have a formula for half-life, and that formula here is, so my notation, I use half-life once again is the time it takes, right? So I use the notation t sub 1/2 right here. T sub 1/2 is to indicate the time the half-life, the time it takes to get half remaining. Okay, so half-life is always equals to natural log of 2 divided by k. And once again, as a quick explanation, this k right here is our growth rate or decay rate. It's the rate for decay, okay, in this particular concept right here. So once again, fortunately, we do have this formula to quickly compute the half-life. And so now with this formula right here, we are totally independent with the population size at the time or anything like that. All we need for this population here is the k. Now, and also we have learned in class about natural log of 2 is actually a number, right? I mean, you can always compute natural log of 2. This is natural log of 2 right here, and it's, the value I believe is to be 0.691 or something like that, but it's always a number, it's always a constant. So we have a constant natural log of 2 divided by k, right? And that's the formula to find out how much half-life that is, how much time it takes.